Welcome to Chapter 6, where we're going to be learning about the Solow growth model. This is the first application of a model that we'll be doing in this course. And, well, without any further ado, let's just get started. Before we go any further, I do want to say this lecture is going to be somewhat math intensive. You are not going to need to know how to do all of the math that I'm walking you through. I'm kind of walking you through this math so you can sort of see how I'm getting to the result that I am. So I'm deriving it for you. Now, that said, there are a couple of equations along the way that you will need to know how to use. So you won't need to know how to do all these steps to get to the solutions of the model, but you will need to know what some of the equations mean, and especially what the variables are, what they mean, and how changing them can affect some of the relationships that we're seeing within the model. So this isn't the most this course isn't going to be super math intensive. However, you will be seeing some math along the way. With that out of the way, we learned about growth and stuff like that in the last chapter. But what we really learned about was just kind of that these things happen, right? Economies grow. Why do they grow? Well, they grow because they grow. Now what we're going to do is we're going to look at a model that analyzes the long-run growth and development behavior, and then eventually we'll try to see, does this fit the data? Does it not fit the data? But along the way, we're going to be seeing how and why these economies grow, not just that they grow. So you kind of get your hands dirty in this. It's going to be a lot of fun. And the Solow model mostly explains how and why these economies grow. It's not the best model out there, but it's a good stepping stone into economic modeling and understanding the way that these models work. So as we go through this model, we're going to be learning both graphically and analytically how to analyze and solve the model. Now, there is a little bit of calculus here, not much, but you won't need to use any of it. So don't think like, if I'm taking derivatives and things like that in here, that you're going to need to know how to do that for the exam. You're not. It's just me explaining how we get to the results that we do, because I'm not really a fan of just going, well, here's a result, and if you want to know why the result is the way it is, well, don't worry about it. Like, I would rather show you guys. So to get started with the model, we know that there are substantial income differences across countries, right? Some countries are really rich. Some countries are really poor. Some countries are kind of in the middle. They're not super rich. They're not super poor. But on top of that, there are totally different growth rates across countries and over time. And again, this is because some countries are poor and catching up. Some are rich and are already caught up or are kind of leading the pack, so to speak. Some aren't really growing at all. And you just get a lot of stuff in between. So if we see all these different growth rates and we see these different incomes, there got to be a lot of substantial differences across these countries to explain why, right? What factors are really driving this? And if we look at, say, real GDP over time, we'll see some kind of funny looking numbers, right? So looking at mean per capita income, this YPC, looking at mean per capita income, right? In 1960, it was about $3,900 up to 2005, where it was almost $13,000. So mean per capita incomes are increasing, right? But the spread is increasing somewhat substantially, as well as the ratio of the highest and lowest, like the top 90th and the lowest 10th percentiles. So income per capita is growing over time, which is good, but that spread's increasing. The richest 90th percentile divided by the 10th percentile is also increasing, indicating that not everybody's getting richer. Right? So what gives? Well, I guess it's time to go play with some numbers and figure it all out. Let's go. Now, there aren't too many assumptions that we're going to be placing on the model here. We will be assuming that the household exists, but it's not explicitly modeled here. So we do know that they exist, but they are going to be devoting an exogenous fraction of their incomes, lowercase s, and the 0-1 interval. So it can be 0, it can be 1. It's just the share of their income that they're going to be saving. And this is done regardless of what's happening in the economy. Now, firms also have access to the same production technology. So there can be like a plethora of firms, and they all have access to what you see in equation 1, right? This is the aggregate production function that we've seen from the chapter on GDP. And what we want is this to be an effective labor units, right? So like per capita labor units. Now, I'm kind of flying through this stuff because you're not really going to need to know how to do this. What I'm doing is I'm just going to divide both sides by L, and then thanks to the magic of mathematics and the fact that this function is homogeneous of degree 1, we get this lowercase y equals lowercase a times kt to the alpha. All right, so this is an output function that is per capita, or per effective labor unit, per worker. Now, like I said, we know the economy saves a constant fraction of its income, which is that lowercase s. Now, per capita investment, this lowercase I, is equal to savings. So that tells me savings is equal to investment, and if it's equal to investment, right, investment is equal to that fraction of income multiplied by income. So it tells me per capita investment is equal to per capita savings. Kind of nice. Now, per capita investment is defined by the law of motion of capital. And it is investment I equal to KT plus 1, future capital, right? The next period's capital, minus 1 minus delta times today's capital. What is this? Well, that 1 minus delta, right, is accounting for depreciation of physical capital that we have today. So if delta is, say, 0.05, right, depreciation is 5%, then that's going to tell me 95%, right, 1 minus 0.05, 95% of today's capital will exist tomorrow. That means 5% of that capital falls apart and needs to be replaced before we begin adding new units of capital that can be used for production. So equation 3 describes the flow of investment in the economy. And it says investment is defined by the flow of capital less depreciation. And the flow of capital is obviously implying that it changes over time. There's today's capital stock, K sub t, tomorrow's capital stock, KT plus 1, and the more capital we put in, the more the difference in capital between time periods is, and the more investment is. Why is that? Well, KT plus 1 could, suppose it's either 100 or 1,000, right? If KT is stuck at 90 today, which it is, we'll get into why in a second, which would have the larger investment? KT plus 1 equals 100, or KT plus 1 equals 1,000. Well, it'd be 1,000, right? So we can change KT plus 1, right? It can be whatever we want. But we can't change KT because it was stuck at 90, right? That makes current capital at KT a state variable. And the next period's capital, KT plus 1, is what's known as a choice variable. Now, a state variable describes the state of the economy at time t and cannot be changed. A choice variable, right, is a variable that we can choose. KT plus 1 can be chosen. So because we can choose what KT plus 1 is, it's a choice variable. So we can't change what capital currently is, but we can change what capital will be tomorrow. So we can't change today, but I can change tomorrow. And that's what links the savings decisions today to production or output tomorrow, because I choose KT plus 1 today by investing or saving more, right? Remember, investment and savings are equal. So if I invest more today, I get more KT plus 1. And that means tomorrow in period t plus 1, right, I've got YT plus 1 equals AT plus 1 times KT plus 1 to the alpha. Well, there's KT plus 1 right there in equation 4. So I choose it today, and then tomorrow's production increases. So it's a dynamic relationship. Now, to make it simple here, any equation's dynamic if there's more than one time period in it, right? If there is a way to connect two time periods mathematically, then it's a dynamic relationship. So what's this depreciation crap that we see, that delta, right? Well, depreciation tells me how much of the capital is falling apart over time. The higher the rate of depreciation, the more capital is going to fall apart, and the more investment we're going to need just to keep up with the economy, to keep everything constant. So if delta is equal to 0.05, 95% of the capital that we have today will still exist tomorrow. 5% we had today will have fallen apart and need to be replaced. Now, if delta goes up to 10%, right, that means only 90% of the existing capital stock would exist tomorrow. So we would need to invest more just to keep the economy going at the same pace. Okay, cool. So we've actually seen 3 equations already, or at least 3 useful equations. Equations 5, 6, and 7. We've got output as a function of capital, and it's per capita output as a function of per capita capital. I have investment in physical capital. It explains the flow in capital over time. And then I've got the fact that savings equals investment. And I'm going to be using these guys to solve out the model. Mostly. There's still one more equation that we need to see. So why do we want to solve it out, aside from, we want to get a good grade in this course? Well, we want to know what values of capital will give us solutions such that we can maximize output. And from there, we can see how much we invest and how much we consume. By getting these, we learn about what the variable behavior is like and what it's like in a steady state. What the hell is a steady state? Well, essentially, a steady state is like a dynamic equilibrium. Think of it like the variables are at rest over time. They're not changing over time, right? We can get it into that nice steady state, not changing over time. We can see what happens if we were to change savings or capital share of output, that little alpha term, or depreciation, delta, the existing capital stock. We can see how the entire system responds. Now, what would be responding? Well, we would obviously have steady state capital responding. We would have investment, we would have output, and we would have consumption. But we haven't seen an equation with consumption yet, have we? Because right now we've got 3 equations and 4 unknowns, right? The 3 equations that we saw, output, the law of motion of capital, investment, and then the fact that savings equals investment. But I got like 4 unknowns here. I got capital, output, investment, and consumption. And consumption is the variable that we haven't seen yet, and it needs to be accounted for. Just remember, we can either consume or save. And if we save a certain amount, then the rest gets consumed. But we need a relationship to explain that to us, right? You can't just go, oh, well, it is as it is, and then assume everything will work out mathematically. It won't, right? You need an equation to say it. So we use what's known as a resource constraint, y equals c plus I. Now, does that look a little familiar? Maybe add a plus g at the end of it. Y equals c plus I plus g. Oh, that's GDP, isn't it? Yep. Kind of cool, isn't it? It's also a constraint in this model. Now, there's no government in this model. And because there's no government, we're not adding g to it because g is equal to 0. Right? You can add 0 as many times as you want to any equation. You're not getting anything from it. So now, with equation 8, we got 4 equations and 4 unknowns. Hey, cool. We can now get unique solutions to all the variables that we got. Before we go any further, though, let's take a minute to explain what's going on. So we got an equation for output as a function of capital. It's per capita, right, or per person. We want to know how capital, output, investment, and consumption are all going to work together. And if there's an optimal investment amount that maximizes output and doesn't introduce any inefficiencies in consumption, then, well, cool, works out. And then we can look at the causes or drivers of economic growth in the model and see how it shifts production around, which will then let us look at real-world data and see if the data fits the solutions to the model. And we'll see if the solutions explain economic growth all that well. Maybe it does, maybe it doesn't. Got to stick around to find out. Now, maybe this is going to make a little bit more sense graphed out, right? You've seen a lot of equations. You're going, I don't even know what the hell these things look like. So let's graph some stuff out, get a little bit of intuition in terms of what the model looks like. All right, well, here's production, right? Output is a function of capital. We've seen this before, right? We've seen that shape, and we've seen output solely as a function of capital. So this is our production function. Right? Now that production function has a slope. The slope of that production function is what's known as the marginal product of capital, or MPK. And it's given by the first derivative of the production function. All right, so if you take the first derivative of that, you get 1/2 times A times KT to the minus 1/2. And that tells us how much output's increasing by if we were to add one additional unit of capital from some arbitrary starting point, call it K0. And it tells us how much output changes at the margin, right, which as economists is something that we're interested in. So it's a question really of how productive is the next unit of capital. If I add one more unit of capital, will my output increase by a lot or is it going to increase by a little? And it's going to tell us if it's worth to invest more or if it's not really that worth it or that like super worth it, right? We'll see. That's what the marginal product of capital is telling me. If I get this next unit of capital, is it going to be worth it for me to do so? Or do I want to just say, you know what, screw it, not worried about it? Marginal product capital tells me that. Now, it gives me a tangent line at every point. And if you see here, right, you look at this, this function's nonlinear, right? So because it's nonlinear, it's never going to be a straight line. So it's giving me a tangent line at that point. And that tangent line is the slope of the function at that one particular point, and that is the marginal product of capital. So if capital was either 10, 20, right, what would the marginal product of capital be? Now it says KT equals 10, 20, and then 10. I think I meant to do 10, 20, and 100. So anyways, let's just start with KT equals 10. What I can do is I can plug that into the marginal product of capital, right? And it's going to give me 0.158, which tells me if I increased capital a little bit, output would increase by 0.158. Now let's see what the marginal product of capital is when capital is at 20, right? So instead of plugging in 10, I'm going to plug in 20. Okay, I get 0.112. Well, 0.158 when capital is lower, capital is higher, marginal product of capital is lower. Output increased by 0.112 instead of 0.158, which says when we increase capital, the marginal product of capital fell. Now, it was still positive, meaning output still increased, right? But the amount it increased by was less. So let's see what happens when capital is 100. Plug that in. Well, now I get 0.05. Holy shikeys. Okay, so output's getting smaller, or it's increasing by less and less and less. Output's always increasing, right? Because that 0.05 gets added to the production function. But it's increasing it by way less than if output, or if capital was at 20, or if it was at 10. So as capital increases, we see the output increases, but it does so a little less the more we add. This is what's known as the diminishing marginal product of capital. And what it means is that when we add more capital, output's always going to increase, but it increases by less and less for every additional unit of capital that we add. If you like calculus, more calculus, we can see the marginal product of capital is diminishing by taking the derivative of the marginal product of capital, which is really the second derivative of the production function. And if I take that second derivative and evaluate it out, I get negative 1/4 times A times K to the negative 3/2. So for any positive value of K, that guy is going to be negative, right? Which tells me there's a diminishing marginal product of capital. So output's increasing at a decreasing rate. Hence, the slope, you can see it's increasing, albeit at a decreasing rate. So now that we've learned a lot about the production function, let's learn a little bit about investment, right? And it's governed by what's known as the law of motion of capital. We've gone through this already, but a little bit of refresher from earlier in the lecture is not really a bad thing. It describes the flow in capital from one period to the next. And if I add more capital to the economy, right, then KT plus 1 will go up, which increases the difference between tomorrow's and today's capital, which thus increases investment. Now, investment's equal to savings, right? Well, yeah, it is. And remember, savings is a constant fraction of output. So investment is a constant fraction of output. And what I can do is I can graph it out in capital and output space. And because it's a constant fraction of output, it's really just a scaled down version of output, which tells me S times Y is equal to I, which is equal to the law of motion of capital. Right? So the black curve here is output, that's production. The blue is investment. Now it looks just like the output curve, right? Yeah, except it's shrunken down a little bit. It's shrunken down by S, because remember, S is between 0 and 1. So S is a decimal, it's a fraction. So it's going to be scaling output down. So let's say here savings is 0.5, right? Well, if that's the case, the investment curve is going to be literally half as high as the output curve. Now, if savings is like 0.05, right, 5%, it will literally be 5% as high as output. So all it's doing is just scaling it down. Now, fun little story time with Jeremy. The first time I ever taught this model to a class was like 6 years ago, I think. I think it was 6 years ago when I was still in grad school. And I wanted to see how GDP changed given changes in depreciation. And, well, to see it, I just substitute investment into GDP. So let's start with the equation for GDP, get y equals c plus I. And I'm going to substitute the law of motion of capital in for I. And when I did that, I get y equals c plus kt plus 1 minus 1 minus delta times kt. And at this point, somebody asked me how output would change if depreciation increased. And I said it would fall, which it will. But when I plugged a larger value in for depreciation, I ended up finding investment increased, which would have meant that GDP increased. And I was like really confused by this. Well, it turns out there's a little bit of an issue because investment would increase, but the amount of capital it was replacing also increased, which means you saw a high investment rate, but it wasn't the result of people wanting to save more. Instead, it was the result of the capital stock falling apart faster. So if delta increases, investment will increase, but it's because we need to replace all the existing capital that's falling apart and isn't actually adding to output. So, a little oopsie on my part, something that is definitely worth considering, because if it's something that I can make a mistake on, surely everybody else can make a mistake on it too. So I just wanted to make it known that this could be something that, if you're working through it and you're like, wait a minute, how does this, what the hell's going on? That's why. Now, maybe I'm the only person in the world that made that mistake. Also, very likely, I made a lot of mistakes when I was in grad school. I was there for a while. But, maybe, maybe not. We'll see. Moving on. Now, so in the earlier slide, I substituted out investment for the flow of capital over time, which gave me y equals c plus kt plus 1 minus 1 minus delta times k. But I can actually go a little further than this, right? What I can also do is I can substitute the production function, a times k to the alpha, in for y. And then it gives me a times k to the alpha equals c plus kt plus 1 minus delta times kt. Now what I've done here is I've substituted out a lot of endogenous variables. I got rid of y, output, and I got rid of investment, I. Now they're still in the equation technically, right? It's just I've substituted what they're equal to into that equation. And when we get to solving this guy, which isn't going to be done in this lecture, it'll be done in the next lecture, you'll see it's actually much easier to play with because, well, if we look at that equation right there, I can basically get consumption on one side and all the capital variables on the other side of the equation. Now I've got consumption as a function of capital. And when I solve for my steady states and stuff, it gets very, very easy to work out. So let's go back to something, right? Because I've got consumption here. Remember, investment's a constant share of output, so I equals S times Y. And if that's the case, right, and S is between 0 and 1, then consumption would be 1 minus S times Y. So in this case, well, consumption is equal to 1 minus S times A times K to the alpha, right? Because Y equals A times K to the alpha. So I can plug that in for consumption. And now this resource constraint is entirely in terms of capital over time. And this is actually even easier to solve out analytically. It's kind of cool. So what we're going to do when we solve this, right? Now that you've seen the functions, you've seen the equations, what we can now do is we can solve it out graphically. When we do it graphically, I'll then go back and solve it out analytically, and then hopefully that'll kind of tie some things together and make some stuff make sense. But looking at it analytically first is something that we can use to help us kind of conceptualize how we graph the output, which then gives us investment, depreciation, all that cool stuff in the same graph, so that they're all functions of capital. Output is a function of capital in some way, shape, or form. Now, beyond that, we are going to hold on to the equations just for right now. And once we're done with finding the graphical solution, like I said, we're going to return to these equations and solve them out. Now, at this point, I've probably tapped out on all the math and stuff. Could go further, but I don't really see what the point is. So we're going to end it here, solve out the model next week. Now, a little teaser for the model. We're going to have a line to graph out that explains depreciation in capital and output space. And then from there, we get our optimal values for capital, get optimal values for output, investment, and consumption. And then we can learn about how to introduce economic growth, which is that AT term, right? That's where the source of new ideas comes from. But that's for next week. It's not for this week. So all that said, we're done. Peace out. Have a great weekend.